The Ethereum White Paper. Hey. What's up, everybody? It's Giovanni Pickle. Follow me on Twitter. Please hit that like button. Hit subscribe if you want to be notified of when I post more white papers. And if you're feeling generous and feel like you derive some value out of this recording, you can always drop a little something in my tip jar. This white paper is a lot to take in, especially if you don't have any computer coding type of background. There's a number of times throughout here that it gets into some code or equations, and I'm just going to do my best to read it as I see it, even if I don't know how it's supposed to be read. There's sometimes where I'll just skip over the code because it's either negligible or inappropriate for audio format, and you can just check it out in the white paper. You know, I don't even understand every single piece of it, but just powering through it, it really did help me to grasp the concepts a little bit better. A couple last things of note. The Ethereum white paper is posted on their GitHub page, and they do occasionally update it, so just keep in mind this recording was made in mid-March 2018. There's also a short history of and introduction to blockchain and Bitcoin at the beginning of the Ethereum white paper. I chose to omit that for the audiobook recording as I think it's redundant in that regard, and you can always check out the Bitcoin white paper and look online to find any of that information. So I just wanted to dive right into Ethereum, which is what we're here for. Anyway, this one's gonna take some focus. Let's do it. Ethereum. The intent of Ethereum is to create an alternative protocol for building decentralized applications, providing a different set of trade-offs that we believe will be very useful for a large class of decentralized applications, with particular emphasis on situations where rapid development time, security for small and rarely used applications, and the ability of different applications to very efficiently interact are important. Ethereum does this by building what is essentially the ultimate abstract foundational layer, a blockchain with a built-in Turing-complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership, transaction formats, and state transition functions. A bare-bones version of Namecoin can be written in 2 lines of code, and other protocols like currencies and reputation systems can be built in under 20. Smart contracts, cryptographic boxes that contain value and only unlock it if certain conditions are met, can also be built on top of the platform, with vastly more power than that offered by Bitcoin scripting because of the added powers of Turing completeness, value awareness, blockchain awareness, and state. Ethereum Accounts. In Ethereum, the state is made up of objects called accounts, with each account having a 20-byte address and state transitions being direct transfers of value and information between accounts. An Ethereum account contains 4 fields. The nonce, a counter used to make sure each transaction can only be processed once. The account's current ether balance. The account's contract code, if present. The account's storage, empty by default. Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. In general, there are 2 types of accounts: externally owned accounts controlled by private keys and contract accounts controlled by their contract code. An externally owned account has no code, and one can send messages from an externally owned account by creating and signing a transaction. In a contract account, every time the contract account receives a message, its code activates, allowing it to read and write to internal storage and send other messages or create contracts in turn. Note that contracts in Ethereum should not be seen as something that should be fulfilled or complied with. Rather, they are more like autonomous agents that live inside of the Ethereum execution environment, always executing a specific piece of code when poked by a message or transaction, and having direct control of their own ether balance and their own key/value store to keep track of persistent variables. Messages and transactions. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain The recipient of the message. A signature identifying the sender. The amount of ether to transfer from the sender to the recipient. An optional data field. A start gas value representing the maximum number of computational steps the transaction execution is allowed to take. A gas price value representing the fee the sender pays per computational step. The first three are standard fields expected in any cryptocurrency. The data field has no function by default, but the virtual machine has an opcode using which a contract can access the data. As an example use case, if a contract is functioning as an on-blockchain domain registration service, then it may wish to interpret the data being processed to it as containing two fields, the first field being a domain to register and the second field being the IP address to register it to. The contract would read these values from the message data and appropriately place them in storage. The start gas and gas price fields are crucial for Ethereum's anti-denial of service model. In order to prevent accidental or hostile infinite loops or other computational wastage in code, each transaction is required to set a limit to how many computational steps of code execution it can use. The fundamental unit of computation is gas. Usually, a computational step costs 1 gas, but some operations cost higher amounts of gas because they are more computationally expensive or increase the amount of data that must be stored as part of the state. There is also a fee of 5 gas for every byte in the transaction data. The intent of the fee system is to require an attacker to pay proportionately for every resource that they consume, including computation, bandwidth, and storage. Hence, any transaction that leads to the network consuming a greater amount of any of these resources must have a gas fee roughly proportional to the increment. Messages. Contracts have the ability to send messages to other contracts. Messages are virtual objects that are never serialized and exist only in the Ethereum execution environment. A message contains the sender of the message, implicit, the recipient of the message, the amount of ether to transfer alongside the message, an optional data field, a start gas value. Essentially, a message is like a transaction, except it is produced by a contract and not an external actor. A message is produced when a contract currently executing code executes the call opcode, which produces and executes a message. Like a transaction, a message leads to the recipient account running its code. Thus, contracts can have relationships with other contracts in exactly the same way that external actors can. Note that the gas allowance assigned by a transaction or contract applies to the total gas consumed by that transaction and all sub-executions. For example, if an external actor A sends a transaction to B with 1,000 gas, and B consumes 600 gas before sending a message to C, and the internal execution of C consumes 300 gas before returning, then B can spend another 100 gas before running out of gas. Ethereum State Transition Function. The Ethereum State Transition Function can be defined as follows. 1. Check if the transaction is well informed, i.e. has the right number of values. The signature is valid, and the nonce matches the nonce in the sender's account. If not, return an error. 2. Calculate the transaction fee as start gas times gas price, and determine the sending address from the signature. Subtract the fee from the sender's account balance and increment the sender's nonce. If there is not enough balance to spend, return an error. 3. Initialize gas equals start gas and take off a certain quantity of gas per byte to pay for the bytes in the transaction. 4. Transfer the transaction value from the sender's account to the receiving account. If the receiving account does not yet exist, create it. If the receiving account is a contract, run the contract's code either to completion or until the execution runs out of gas. 5. If the value transfer failed because the sender did not have enough money or the code execution ran out of gas, revert all state changes except the payment of the fees and add the fees to the miner's account. 6. Otherwise, refund the fees for all remaining gas to the sender and send the fees paid for gas consumed to the miner. For example, suppose that the contract's code is, here it shows some code you can see in the white paper, Note that in reality, the contract code is written in the low-level EVM code. This example is written in Serpent, one of our high-level languages, for clarity, and can be compiled down to EVM code. Suppose that the contract's storage starts off empty, and a transaction is sent with 10 Ether value, 2,000 gas, 0.001 Ether gas price, and 64 bytes of data, with bytes 0 through 31 representing the number 2, and bytes 32 through 63 representing the string Charlie. The process for the state transition function in this case is as follows. 1. Check that the transaction is valid and well-formed. 2. Check that the transaction sender has at least 2,000 times 0.001, which equals 2 Ether. If it is, then subtract 2 Ether from the sender's account. 3. Initialize gas equals 2,000. Assuming the transaction is 170 bytes long and the byte fee is 5, subtract 850 so that there is 1,150 gas left. 4. Subtract 10 more Ether from the sender's account and add it to the contract's account. 5. Run the code. In this case, this is simple. It checks if the contract's storage at index 2 is used, notices that it is not, and so it sets the storage at index 2 to the value Charlie. Suppose this takes 187 gas, so the remaining amount of gas is 1,150 minus 187, which equals 963. 6. Add 963 times 0.001, which equals 0.963 Ether, back to the sender's account and return the resulting state. If there was no contract at the receiving end of the transaction, then the total transaction fee would simply be equal to the provided gas price multiplied by the length of the transaction in bytes, and the data sent alongside the transaction would be irrelevant. Note that the messages work equivalently to transactions in terms of reverts. If a message execution runs out of gas, then that message's execution and all other executions triggered by that execution revert, but parent executions do not need to revert. This means that it is safe for a contract to call another contract, as if A calls B with G gas, then A's execution is guaranteed to lose at most G gas. Finally, note that there is an opcode create that creates a contract. Its execution mechanics are generally similar to call, with the exception that the output of the execution determines the code of a newly created contract. Code execution. The code in Ethereum contracts is written in a low-level, stack-based bytecode language referred to as Ethereum Virtual Machine Code, or EVM code. The code consists of a series of bytes where each byte represents an operation. In general, code execution is an infinite loop that consists of repeatedly carrying out the operation at the current program counter, which begins at 0, and then incrementing the program counter by 1 until the end of the code is reached or an error or stop or return instruction is dedicated. The operations have access to 3 types of space in which to store data. The stack, a last-in, first-out container to which values can be pushed and popped. Memory, an infinitely expandable byte array. The contract's long-term storage, a key/value store. Unlike stack and memory, which reset after computation ends, storage persists for the long term. The code can also access the value, sender, and data of the incoming message, as well as block header data, and the code can also return a byte array of data as an output. The formal execution model of EVM code is surprisingly simple. While the Ethereum virtual machine is running, its full computational state can be defined by the tuple block state, transaction, message, code, memory, stack, PC, gas, where block state is the global state containing all accounts and includes balances and storage. At the start of every round of execution, the current instruction is found by taking the, here's some sort of math computer code that I don't understand, and each instruction has its own definition in terms of how it affects the tuple. For example, add pops 2 items out the stack and pushes their sum, reduces gas by 1, and increments PC by 1. And sStore pops the top 2 items off the stack and inserts the second item into the contract's storage at the index specified by the first item. Although there are many ways to optimize Ethereum virtual machine execution via just-in-time compilation, a basic implementation of Ethereum can be done in a few hundred lines of code. Blockchain and mining. The beginning of this section starts off with a blockchain diagram you can see in the white paper. The Ethereum blockchain is in many ways similar to the Bitcoin blockchain, although it does have some differences. The main difference between Ethereum and Bitcoin with regard to the blockchain architecture is that, unlike Bitcoin, Ethereum blocks contain a copy of both the transaction list and the most recent state. Aside from that, 2 other values, the block number and the difficulty, are also stored in the block. The basic block validation algorithm in Ethereum is as follows. 1. Check if the previous block referenced exists and is valid. 2. Check that the timestamp of the block is greater than that of the referenced previous block and less than 15 minutes into the future. 3. Check that the block number, difficulty, transaction root, uncle root, and gas limit, various low-level Ethereum-specific concepts, are valid. 4. Check that the proof of work on the block is valid. 5. Let S0 be the state at the end of the previous block. 6. Let TX be the block's transaction list with n transactions. Here it shows a line of code. If any applications returns an error, or if the total gas consumed in the block up until this point exceeds the gas limit, return an error. 7. Let S final be SN, but adding the block reward paid to the miner. 8. Check if the Merkle tree root of the state S final is equal to the final state root provided in the block header. If it is, the block is valid. Otherwise, it is not valid. The approach may seem highly inefficient at first glance because it needs to store the entire state with each block, but in reality, efficiency should be comparable to that of Bitcoin. The reason is that the state is stored in the tree structure, and after every block, only a small part of the tree needs to be changed. Thus, in general, between 2 adjacent blocks, the vast majority of the tree should be the same, and therefore the data can be stored once and referenced twice using pointers, i.e. hashes of subtrees. A special kind of tree, known as a Patricia tree, is used to accomplish this, including a modification to the Merkle tree concept that allows for nodes to be inserted and deleted and not just changed efficiently. Additionally, because all of the state information is part of the last block, there is no need to store the entire blockchain history. A strategy which, if it could be applied to Bitcoin, can be calculated to provide 5 to 20 times savings in space. A commonly asked question is where contract code is executed in terms of physical hardware. This has a simple answer. The process of executing contract code is part of the definition of the state transition function, which is part of the block validation algorithm. So if a transaction is added into block B, the code execution spawned by that transaction will be executed by all nodes, now and in the future, that download and validate block B. Applications. In general, there are 3 types of applications on top of Ethereum. The first category is financial applications, providing users with more powerful ways of managing and entering into contracts using their money. This includes subcurrencies, financial derivatives, hedging contracts, savings wallets, wills, and ultimately even some classes of full-scale employment contracts. The second category is semi-financial applications, where money is involved, but there is also a heavy non-monetary side to what is being done. A perfect example is self-enforcing bounties for solutions to computational problems. Finally, there are applications such as online voting and decentralized governance that are not financial at all. Token systems. On-blockchain token systems have many applications, ranging from subcurrencies representing assets such as USD or gold to company stocks, individual tokens representing smart property, secure, unforgeable coupons, and even token systems with no ties to conventional value at all, used as point systems for incentivization. Token systems are surprisingly easy to implement in Ethereum. The key point to understand is that all a currency or token system fundamentally is a database with one operation. Subtract X units from A and give X units to B with the proviso that 1. A had at least X units before the transaction, and 2. The transaction is approved by A. All that it takes to implement a token system is to implement this logic into a contract. The basic code for implementing a token system in Serpent looks as follows. Here it shows a few lines of code in the white paper. This is essentially a literal implementation of the banking system state transition function described further above in this document. A few extra lines of code need to be added to provide for the initial step of distributing the currency units in the first place and a few other edge cases. And ideally, a function would be added to let other contracts query for the balance of an address. But that's all there is to it. Theoretically, Ethereum-based token systems acting as sub-currencies can potentially include another important feature that on-chain, Bitcoin-based metacurrencies lack: the ability to pay transaction fees directly in that currency. The way this would be implemented is that the contract would maintain an Ether balance with which it would refund Ether used to pay fees to the sender, and it would refill this balance by collecting the internal currency units that it takes in fees and reselling them in a constant running auction. Users would thus need to activate their accounts with Ether, but once the Ether is there, it would be reusable because the contract would refund it each time. Financial derivatives and stable-value currencies. Financial derivatives are the most common application of a smart contract and one of the simplest to implement in code. The main challenge in implementing financial contracts is that the majority of them require reference to an external price ticker. For example, a very desirable application is a smart contract that hedges against the volatility of Ether, or another cryptocurrency, with respect to the US dollar. But doing this requires the contract to know what the value of ETH/USD is. The simplest way to do this is through a data feed contract maintained by a specific party, for example, NASDAQ, designed so that that party has the ability to update the contract as needed, and providing an interface that allows other contracts to send a message to that contract and get back a response that provides the price. Given that critical ingredient, the hedging contract would look as follows. 1. Wait for party A to input 1,000 Ether. 2. Wait for party B to input 1,000 Ether. 3. Record the USD value of 1,000 Ether calculated by querying the data feed contract in storage. Say this is X amount of dollars. 4. After 30 days, allow A or B to reactivate the contract in order to send X amount of dollars worth of Ether, calculated by querying the data feed contract again to get the new price, to A and the rest to B. Such a contract would have significant potential in crypto commerce. One of the main problems cited about cryptocurrency is the fact that it's volatile. Although many users and merchants may want the security and convenience of dealing with cryptographic assets, they may not wish to face that prospect of losing 23% of the value of their funds in a single day. Up until now, the most commonly proposed solution has been issuer-backed assets. The idea is that an issuer creates a subcurrency in which they have the right to issue and revoke units, and provide 1 unit of the currency to anyone who provides them offline with 1 unit of a specified underlying asset, for example, gold or USD. The issuer then promises to provide 1 unit of the underlying asset to anyone who sends back 1 unit of the crypto asset. This mechanism allows any non-cryptographic asset to be uplifted into a cryptographic asset, provided that the issuer can be trusted. In practice, however, issuers are not always trustworthy, and in some cases, the banking infrastructure is too weak or too hostile for such services to exist. Financial derivatives provide an alternative. Here, instead of a single issuer providing the funds to back up an asset, a decentralized market of speculators betting that the price of a cryptographic reference asset, for example ETH, will go up, plays that role. Unlike issuers, speculators have no option to default on their side of the bargain because the hedging contract holds their funds in escrow. Note that this approach is not fully decentralized because a trusted source is still needed to provide the price ticker. Although arguably, even still, this is a massive improvement in terms of reducing infrastructure requirements. Unlike being an issuer, issuing a price feed requires no licenses and can likely be categorized as free speech, and reducing the potential for fraud. Identity and reputation systems. The earliest alternative cryptocurrency of all, Namecoin, attempted to use a Bitcoin-like blockchain to provide a name registration system where users can register their names in a public database alongside other data. The major cited use case is for a DNS system, mapping domain names like bitcoin.org, or in Namecoin's case, bitcoin.bit, to an IP address. Other use cases include email authentication and potentially more advanced reputation systems. Here's the basic contract to provide a Namecoin-like registration system on Ethereum. Here it shows a small amount of code. The contract is very simple. All it is a database inside the Ethereum network that can be added to but not modified or removed from. Anyone can register a name with some value, and that registration then sticks forever. A more sophisticated name registration contract will also have a function clause, allowing other contracts to query it, as well as a mechanism for the owner, i.e. the first registerer, of a name to change the data or transfer ownership. One can even add reputation and web of trust functionality on top. Decentralized file storage. Over the past few years, there have emerged a number of popular online file storage startups, the most prominent being Dropbox, seeking to allow users to upload a backup of their hard drive and have the service store that backup and allow the user to access it in exchange for a monthly fee. However, at this point, the file storage market is at times relatively inefficient. A cursory look at various existing solutions shows that particular at the uncanny valley 200 to 200 gigabyte level, at which neither free quotas nor enterprise level discounts kick in, monthly prices for mainstream file storage costs are such that you are paying for more than the cost of the entire hard drive in a single month. Ethereum contracts can allow for the development of a decentralized file storage ecosystem where individual users can earn small quantities of money by renting out their own hard drives, and unused space can be used to further drive down the costs of file storage. The key underpinning piece of such a device would be what we have termed the decentralized Dropbox contract. This contract works as follows. First, one splits the desired data up into blocks, encrypting each block for privacy, and builds a Merkle tree out of it. One then makes a contract with the rule that, every n blocks, the contract would pick a random index in the Merkle tree, using the previous block hash accessible from contract code as a source of randomness, and give X ether to the first entity to supply a transaction with a simplified payment verification-like proof of ownership of that block at the particular index in the tree. When a user wants to re-download their file, they can use a micropayment channel protocol, for example, pay 1 sabo per 32 kilobytes, to recover the file. The most fee-efficient approach is for the payer to not publish the transaction until the end, instead replacing the transaction with a slightly more lucrative one with the same nonce every 32 kilobytes. An important feature of the protocol is that, although it may seem like one is trusting many random nodes not to decide to forget the file, one can reduce that risk down to near zero by splitting the file into many pieces via secret sharing and watching the contracts to see each piece is still in some node's possession. If a contract is still paying out money, that provides a cryptographic proof that someone out there is still storing the file. Decentralized autonomous organizations. The general concept of a decentralized autonomous organization is that of a virtual entity that has a certain set of members or shareholders which, perhaps with a 67% majority, have the right to spend the entity's funds and modify its code. The members would collectively decide on how the organization should allocate its funds. Methods for allocating a DAO's funds could range from bounties, salaries, to even more exotic mechanisms such as an internal currency to reward work. This essentially replicates the legal trappings of a traditional company or nonprofit, but using only cryptographic blockchain technology for enforcement. So far, much of the talk around DAOs has been around the capitalist model of a decentralized autonomous corporation with dividend-receiving shareholders and tradable shares. An alternative, perhaps, described as a decentralized autonomous community, would have all members have an equal share in the decision-making and require 67% of existing members to agree to add or remove a member. The requirement that one person can only have one membership would then need to be enforced collectively by the group. A general outline for how to code a DAO is as follows. The simplest design is simply a piece of self-modifying code that changes if 2/3 of members agree on a change. Although code is theoretically immutable, one can easily get around this and have de facto mutability by having chunks of the code in separate contracts and having the address of which contracts to call stored in the modifiable storage. In a simple implementation of such a DAO contract, there would be 3 transaction types, distinguished by the data provided in the transaction. 0IKV, to register a proposal with index I to change the address at storage index K to value V. 0I, to register a vote in favor of proposal I. 2I, to finalize proposal I if enough votes have been made. The contract would then have clauses for each of these. It would maintain a record of all open storage changes along with the list of who voted for them. It would also have a list of all members. When any storage change gets to 2/3 of members voting for it, a finalizing transaction could execute the change. A more sophisticated skeleton would also have a built-in voting ability for features like sending a transaction, adding members or removing members, and may even provide for liquid democracy-style vote delegation. For example, anyone can assign someone to vote for them, and assignment is transitive, so if A assigns B and B assigns C, then C determines A's vote. This design would allow the DAO to grow organically as a decentralized community, allowing people to eventually delegate the task of filtering out who is a member to specialists, although unlike in the current system, specialists can easily pop in and out of existence over time as individual community members change their alignments. An alternative model is for a decentralized corporation where any account can have 0 or more shares, and 2/3 of the shares are required to make a decision. A complete skeleton would involve asset management functionality, the ability to make an offer to buy or sell shares, and the ability to accept offers, preferably with an order matching mechanism inside the contract. Delegation would also exist liquid democracy style, generalizing the concept of a board of directors. Further applications. 1. Saving wallets. Suppose that Alice wants to keep her funds safe, but is worried that she will lose or someone will hack her private key. She puts Ether into a contract with Bob, a bank, as follows. Alice alone can withdraw a maximum of 1% of the funds per day. Bob alone can withdraw a maximum of 1% of the funds per day, but Alice has the ability to make a transaction with her key, shutting off this ability. Alice and Bob together can withdraw anything. Normally, 1% per day is enough for Alice, and if Alice wants to withdraw more, she can contact Bob for help. If Alice's key gets hacked, she runs to Bob to move the funds to a new contract. If she loses her key, Bob will get the funds out eventually. If Bob turns out to be malicious, then she can turn off his ability to withdraw. 2. Crop insurance. One can easily make a financial derivatives contract, but using a data feed of the weather instead of any price index. If a farmer in Iowa purchases a derivative that pays out inversely based upon the precipitation in Iowa, then if there is a drought, the farmer will automatically receive money, and if there is enough rain, the farmer will be happy because their crops would do well. This can be expanded to natural disaster insurance generally. 3. A decentralized data feed. For financial contracts for deference, it may actually be possible to decentralize the data feed via a protocol called shelling coin. Shelling coin basically works as follows. N parties all put into the system the value of a given datum, for example, the ETH/USD price. The values are sorted, and everyone between the 25th and 75th percentile gets 1 token as a reward. Everyone has the incentive to provide the answer that everyone else will provide, and the only value that a large number of players can realistically agree on is the obvious default, the truth. This creates a decentralized protocol that can theoretically provide any number of values, including the ETH/USD price, the temperature in Berlin, or even the result of a particular hard computation. 4. Smart multi-signature escrow. Bitcoin allows multi-signature transaction contracts where, for example, 3 out of a given 5 keys can spend the funds. Ethereum allows for more granularity. For example, 4 out of 5 can spend everything, 3 out of 5 can spend up to 10% per day, and 2 out of 5 can spend up to 0.5% per day. Additionally, Ethereum multisig is asynchronous. 2 parties can register their signatures on the blockchain at different times, and the last signature will automatically send the transaction. 5. Cloud computing. The EVM technology can also be used to create a verifiable computing environment, allowing users to ask others to carry out computations and then optionally ask for profits that computations at certain randomly selected checkpoints were done correctly. This allows for the creation of a cloud computing market where any user can participate with their desktop, laptop, or specialized server, and spot checking together with security deposits can be used to ensure that the system is trustworthy. For example, nodes cannot profitably cheat. Although such a system may not be suitable for all tasks, tasks that require a high level of inter-process communication, for example, cannot easily be done on a large cloud of nodes. Other tasks, however, are much easier to parallelize. Projects like SETI at home, folding at home, and genetic algorithms can easily be implemented on top of such a platform. 6. Peer-to-peer gambling. Any number of peer-to-peer gambling protocols, such as Frank Stajano and Richard Clayton's CyberDice, can be implemented on the Ethereum blockchain. The simplest gambling protocol is actually simply a contract for difference on the next block hash, and more advanced protocols can be built up from there, creating gambling services with near zero fees that have no ability to cheat. 7. Prediction markets. Provided an Oracle or Schelling coin, prediction markets are also easy to implement, and prediction markets together with Schelling coin may prove to be the first mainstream application of feudarchy as a governance protocol for decentralized organizations. 8. On-chain decentralized marketplaces using the identity and reputation system as a base. Miscellanea and concerns. Modified Ghost implementation. The greedy, heaviest observed subtree, or GHOST, giving us the acronym GHOST, protocol is an innovation first introduced by Yonatan Sompolinsky and Aviv Zohar in December 2013. The motivation behind Ghost is that blockchains with fast confirmation times currently suffer from reduced security due to a high stale rate. Because blocks take a certain time to propagate through the network, if miner A mines a block and then miner B happens to mine another block before miner A's block propagates to B, miner B's block will end up wasted and will not contribute to network security. Furthermore, there is a centralization issue. If miner A is a mining pool with 30% hash power and B has 10% hash power, A will have a risk of producing a stale block 70% of the time, since the other 30% of the time, A produced the last block and so will get mining data immediately, whereas B will have a risk of producing a stale block 90% of the time. Thus, if the block interval is short enough for the stale rate to be high, A will be substantially more efficient simply by virtue of its size. With these two effects combined, blockchains which produce blocks quickly are very likely to lead to one mining pool having a large enough percentage of the network hash power to have de facto control over the mining process. As described by Sompolinsky and Zohar, Ghost solves the first issue of network security loss by including stale blocks in the calculation of which chain is the longest. That is to say, not just the parent and further ancestors of a block, but also the stale descendants of the block's ancestors, in Ethereum jargon, uncles, are added to the calculation of which block has the largest total proof of working backing it. To solve the second issue of centralization bias, we go beyond the protocol described by Sompolinsky and Zohar and also provide block rewards to stales. A stale block receives 87.5% of its base reward, and the nephew that includes the stale block receives the remaining 12.5%. Transaction fees, however, are not awarded to uncles. Ethereum implements a simplified version of Ghost, which only goes down 7 levels. Specifically, it is defined as follows. A block must specify a parent, and it must specify 0 or more uncles. An uncle included in block B must have the following properties. It must be a direct child of the kth generation ancestor of B, where 2 is less than or equal to k, and k is less than or equal to 7. it cannot be an ancestor of B. An uncle must be a valid block header, but does not need to be a previously verified or even valid block. An uncle must be different from all uncles included in previous blocks and all other uncles included in the same block, non-double inclusion. For every uncle U in block B, the miner of B gets an additional 3.125% added to its Coinbase reward, and the miner of U gets 93.75% of a standard Coinbase reward. This limited version of Ghost, with uncles included only up to 7 generations, was used for 2 reasons. First, unlimited Ghost would include too many complications into the calculation of which uncles for a given block are valid. Second, unlimited Ghost with compensation as used in Ethereum removes the incentive for a miner to mine on the main chain and not the chain of a public attacker. Fees. Because every transaction published into the blockchain imposes on the network the cost of needing to download and verify it, there is a need for some regulatory mechanism, typically involving transaction fees, to prevent abuse. The default approach used in Bitcoin is to have purely voluntary fees, relying on miners to act as the gatekeepers and set dynamic minimums. This approach has been received very favorably in the Bitcoin community, particularly because it is market-based, allowing supply and demand between miners and transaction senders to determine the price. The problem with this line of reasoning is, however, that transaction processing is not a market. Although it is intuitively attractive to construe transaction processing as a service that the miner is offering to the sender, in reality, every transaction that a miner includes will need to be processed by every node in the network, so the vast majority of the cost of transaction processing is borne by third parties and not the miner that is making the decision of whether or not to include it. Hence, tragedy of the commons problems are very likely to occur. However, as it turns out, this flaw in the market-based mechanism, when given a particular inaccurate simplifying assumption, magically cancels itself out. The argument is as follows. Suppose that 1. A transaction leads to K operations, offering the reward KR to any miner that includes it, where R is set by the sender and K and R are, roughly, visible to the miner beforehand. 2. An operation has a processing cost of C to any node, i.e., all nodes have equal efficiency. 3. There are n mining nodes, each with exactly equal processing power, i.e., 1/n of total. 4. No non-mining full nodes exist. A miner would be willing to process a transaction if the expected reward is greater than the cost. Thus, the expected reward is KR/n, since the miner has a 1/n chance of processing the next block, and the processing cost for the miner is simply KC. Hence, miners will include transactions where KR/n is greater than KC or R is greater than NC. Note that R is the per operation fee provided by the sender and is thus a lower bound on the benefit that the sender derives from the transaction, and NC is the cost to the entire network together of processing an operation. Hence, miners have the incentive to include only those transactions for which the total utilitarian benefit exceeds the cost. However, there are several important deviations from those assumptions in reality. 1. The miner does pay a higher cost to process the transaction than the other verifying nodes, since the extra verification time delays block propagation and thus increases the chance the block will become a stale. 2. There do exist non-mining full nodes. 3. The mining power distribution may end up radically inegalitarian in practice. 4. Speculators, political enemies, and crazies whose utility function includes causing harm to the network do exist, and they can cleverly set up contracts where their cost is much lower than the cost paid by other verifying nodes. 1. Provides a tendency for the miner to include fewer transactions, and 2. Increases NC. Hence, these two effects at least partially cancel each other out. 3 and 4 are the major issue. To solve them, we simply institute a floating cap. No block can have more operations than block limit factor times the long-term exponential moving average. Specifically, and here it does a little code math thing, blah, 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 block limit factor, and EMA factor are constants that will be set to 65536 and 1.5 for the time being, but will likely be changed after further analysis. There is another factor disincentivizing large block sizes in Bitcoin. Blocks that are large will take longer to propagate and thus have a higher probability of becoming stales. In Ethereum, highly gas-consuming blocks can also take longer to propagate, both because they are physically larger and because they take longer to process the transaction state transitions to validate. This delayed disincentive is a significant consideration in Bitcoin, but less so in Ethereum because of the Ghost protocol. Hence, relying on regulated block limits provides a more stable baseline. Computation and Turing-Completeness. An important note is that the Ethereum virtual machine is Turing complete. This means that EVM code can encode any computation that can be conceivably carried out, including infinite loops. EVM code allows looping in two ways. First, there is a jump instruction that allows the program to jump back to a previous spot in the code, and a jump I instruction to do conditional jumping, allowing for statements like, here it is a little code math thing. Second, contracts can call other contracts, potentially allowing for looping through recursion. This naturally leads to a problem. Can malicious users essentially shut miners and full nodes down by forcing them to enter into an infinite loop? The issue arises because of a problem in computer science known as the halting problem. There is no way to tell in the general case whether or not a given program will ever halt. As described in the state transition section, our solution works by requiring a transaction to set a maximum number of computational steps that it is allowed to take. And if execution takes longer, computation is reverted, but fees are still paid. Messages work in the same way. To show the motivation behind our solution, consider the following examples. An attacker creates a contract which runs an infinite loop and then sends a transaction activating that loop to the miner. The miner will process the transaction, running the infinite loop, and wait for it to run out of gas. Even though the execution runs out of gas and stops halfway through, the transaction is still valid and the miner still claims the fee from the attacker for each computational step. An attacker creates a very long, infinite loop with the intent of forcing the miner to keep computing for such a long time that by the time computation finishes, a few more blocks will have to come out and it will not be possible for the miner to include the transaction to claim the fee. However, the attacker will be required to submit a value for start gas, limiting the number of computational steps that execution can take. So the miner will know ahead of time that the computation will take an excessively large number of steps. An attacker sees a contract with code of some form, like, here's some code about sending something, and sends a transaction with just enough gas to run the first step, but not the second, i.e. making a withdrawal, but not letting the balance go down. The contract author does not need to worry about protecting against such attacks, because if execution stops halfway through, the changes get reverted. A financial contract works by taking the median of 9 proprietary data feeds in order to minimize risk. An attacker takes over one of the data feeds, which is designed to be modifiable via the variable address call mechanism described in the section on DAOs, and converts it to run an infinite loop, thereby attempting to force any attempts to claim funds from the financial contract to run out of gas. However, the financial contract can set a gas limit on the message to prevent this problem. The alternative to Turing completeness is Turing incompleteness, where jump and jump I do not exist and only one copy of each contract is allowed to exist in the call stack at any given time. With this system, the fee system described and the uncertainties around the effectiveness of our solution might not be necessary, as the cost of executing a contract would be bounded above by its size. Additionally, Turing incompleteness is not even that big a limitation. Out of all the contract examples we have conceived internally, so far only one required a loop, and even that loop could be removed by making 26 repetitions of a one-line piece of code. Given the serious implications of Turing completeness and the limited benefit, why not simply have a Turing incomplete language? In reality, however, Turing incompleteness is far from a neat solution to the problem. To see why, consider the following contracts. Here it has some code for contracts. Now send a transaction to A. Thus, in 51 transactions, we have a contract that takes up 2 to the 50th power computational steps. Miners could try to detect such logic bombs ahead of time by maintaining a value alongside each contract, specifying the maximum number of computational steps that it can take, and calculating this for contracts calling other contracts recursively, but that would require miners to forbid contracts that create other contracts, since the creation and execution of all 26 contracts above could easily be rolled into a single contract. Another problematic point is that the address field of a message is a variable. So in general, it may not even be possible to tell which other contracts a given contract will call ahead of time. Hence, all in all, we have a surprising conclusion. Turing-Completeness is surprisingly easy to manage, and the lack of Turing-Completeness is equally surprisingly difficult to manage unless the exact same controls are in place. But in that case, why not just let the protocol be Turing-complete? Currency and issuance. The Ethereum network includes its own built-in currency, Ether, which serves the dual purpose of providing a primary liquidity layer to allow for efficient exchange between various types of digital assets and, more importantly, of providing a mechanism for paying transaction fees. For convenience and to avoid future argument, see the current MBTC, UBTC, Satoshi debate in Bitcoin, the denominations will be pre-labeled. 1. Wei. 10 to the 12th power, Sabo. 10 to the 15th power, Finny. 10 to the 18th power, Ether. This should be taken as an expanded version of the concept of dollars and cents, or BTC and Satoshi. In the near future, we expect Ether to be used for ordinary transactions, Finny for microtransactions, and Sabo and Wei for technical discussions around fees and protocol implementation. The remaining denominations may become useful later and should not be included in clients at this point. The issuance model will be as follows. Ether will be released in a currency sale at the price of 1,000 to 2,000 Ether per BTC, a mechanism intended to fund the Ethereum organization and pay for development that has been used with success by other platforms such as Mastercoin and NXT. Earlier buyers will benefit from larger discounts. The BTC received from the sale will be used entirely to pay salaries and bounties to developers and invested into various for-profit and non-profit projects in the Ethereum and cryptocurrency ecosystem. 0.099 times the total amount sold, 60,102,216 ETH, will be allocated to the organization to compensate early contributors and pay ETH-denominated expenses before the Genesis block. 0.099 times the total amount sold will be maintained as a long-term reserve. 0.26 times the total amount sold will be allocated to miners per year forever at that point. Here's a small chart showing how different groups will be issued different percentages at launch, after 1 year, and after 5 years. Long-term supply growth rate, %. Despite the linear currency issuance, just like with Bitcoin, over time the supply growth rate nevertheless tends to 0. The two main choices in the above model are 1. The existence and size of an endowment pool, and 2. The existence of a permanently growing linear supply as opposed to a capped supply as in Bitcoin. The justification of the endowment pool is as follows. If the endowment pool did not exist and the linear issuance reduced to 0.217 times to provide the same inflation rate, then the total quantity of Ether would be 16.5% less, and so each unit would be 19.8% more valuable. Hence, in the equilibrium, 19.8% more Ether would be purchased in the sale, so each unit would once again be exactly as valuable as before. The organization would also then have 1.198 times as much BTC, which can be considered to be split into two slices, the original BTC and the additional 0.198 times. Hence, this situation is exactly equivalent to the endowment, but with one important difference. The organization holds purely BTC and so is not incentivized to support the value of the Ether unit. The permanent linear supply growth model reduces the risk of what some see as excessive wealth concentration in Bitcoin and gives individuals living in present and future eras a fair chance to acquire currency units, while at the same time retaining a strong incentive to obtain and hold Ether because the supply growth rate as a percentage still tends to zero over time. We also theorize that because coins are always lost over time due to carelessness, death, etc., and coin loss can be modeled as a percentage of the total supply per year, that the total currency supply in circulation will in fact eventually stabilize at a value equal to the annual issuance divided by the loss rate. For example, at a loss rate of 1%, once the supply reaches 26 times, then 0.26 times will be mined and 0.26 times lost every year, creating an equilibrium. Note that in the future, it is likely that Ethereum will switch to a proof-of-stake model for security, reducing the issuance requirement to somewhere between 0 and 0.05 times per year. In the event that the Ethereum organization loses funding or for any other reason disappears, we leave open a social contract. Anyone has the right to create a future candidate version of Ethereum, with the only condition being that the quantity of Ether must be at most equal to 60,102,216 times 1.198 plus 0.26 times n, where n is the number of years after the Genesis block. Creators are free to crowd sell or otherwise assign some or all of the difference between the POS-driven supply expansion and the maximum allowable supply expansion to pay for development. Candidate upgrades that do not comply with the social contract may justifiably be forked into compliant versions. Mining centralization. The Bitcoin mining algorithm works by having miners compute SHA-256 on slightly modified versions of the block header millions of times over and over again until eventually one node comes up with a version whose hash is less than the target, currently around 2 to the 192nd power. However, this mining algorithm is vulnerable to two forms of centralization. First, the mining ecosystem has come to be dominated by ASICs, application-specific integrated circuits, computer chips designed for, and therefore thousands of times more efficient at, the specific task of Bitcoin mining. This means that Bitcoin mining is no longer a highly decentralized and egalitarian pursuit, requiring millions of dollars of capital to effectively participate in. Second, most Bitcoin miners do not actually perform block validation locally. Instead, they rely on a centralized mining pool to provide the block headers. This problem is arguably worse. As of the time of this writing, the top 3 mining pools indirectly control roughly 50% of processing power in the Bitcoin network, although this is mitigated by the fact that miners can switch to other mining pools if a pool or coalition attempts a 51% attack. The current intent at Ethereum is to use a mining algorithm where miners are required to fetch random data from the state, compute some randomly selected transactions from the last n blocks in the blockchain, and return the hash of the result. This has 2 important benefits. First, Ethereum contracts can include any kind of computation, so an Ethereum ASIC would essentially be an ASIC for general computation, i.e. a better CPU. Second, mining requires access to the entire blockchain, forcing miners to store the entire blockchain and at least be capable of verifying every transaction. This removes the need for centralized mining pools. Although mining pools can still serve the legitimate role of evening out the randomness of reward distribution, this function can be served equally well by peer-to-peer pools with no central control. This model is untested, and there may be difficulties along the way in avoiding certain clever optimizations when using contract execution as a mining algorithm. However, one notably interesting feature of this algorithm is that it allows anyone to poison the well by introducing a large number of contracts into the blockchain specifically designed to stymie certain ASICs. The economic incentives exist for ASIC manufacturers to use such a trick to attack each other. Thus, the solution that we are developing is ultimately an adaptive economic human solution rather than purely a technical one. Scalability. One common concern about Ethereum is the issue of scalability. Like Bitcoin, Ethereum suffers from the flaw that every transaction needs to be processed by every node in the network. With Bitcoin, the size of the current blockchain rests at about 15 gigabytes, growing by about 1 megabyte per hour. If the Bitcoin network were to process Visa's 2,000 transactions per second, it would grow by 1 megabyte per 3 seconds, 1 gigabyte per hour, 8 terabytes per year. Ethereum is likely to suffer a similar growth pattern, worsened by the fact that there will be many applications on top of the Ethereum blockchain instead of just a currency, as is the case with Bitcoin, but ameliorated by the fact that Ethereum full nodes need to store just the state instead of the entire blockchain history. The problem with such a large blockchain size is centralization risk. If the blockchain size increases to, say, 100 terabytes, then the likely scenario would be that only a very small number of large businesses would run full nodes, with all regular users using light SPV nodes. In such a situation, there arises the potential concern that the full nodes could band together and all agree to cheat in some profitable fashion, for example, change the block reward and give themselves BTC. Light nodes would have no way of detecting this immediately. Of course, at least one honest full node would likely exist, and after a few hours, information about the fraud would trickle out through channels like Reddit, but at that point, it would be too late. It would be up to the ordinary users to organize an effort to blacklist the given blocks, a massive and likely infeasible coordination problem on a similar scale as that of pulling off a successful 51% attack. In the case of Bitcoin, this is currently a problem, but there exists a blockchain modification suggested by Peter Todd, which will alleviate this issue. In the near term, Ethereum will use 2 additional strategies to cope with this problem. First, because of the blockchain-based mining algorithms, at least every miner will be forced to be a full node, creating a lower bound on the number of full nodes. Second, and more importantly, however, we will include an intermediate state tree root in the blockchain after processing each transaction. Even if block validation is centralized, as long as one honest verifying node exists, the centralization problem can be circumvented via a verification protocol. If a miner publishes an invalid block, that block must either be badly formatted or the state SN is incorrect. Since S0 is known to be correct, there must be some first states, SI, that is incorrect, where SI-1 is correct. The verifying node would provide the index I along with a proof of invalidity consisting of the subset of Patricia tree nodes needing to process apply SI-1 TXI, some code I don't know how to say. Nodes would be able to use those nodes to run that part of the computation and see that the SI generated does not match the SI provided. Another more sophisticated attack would involve the malicious miners publishing incomplete blocks, so the full information does not even exist to determine whether or not blocks are valid. The solution to this is a challenge response protocol. Verification nodes issue challenges in the form of target transaction indices, and upon receiving a node, a light node treats the block as untrusted until another node, whether the miner or another verifier, provides a subset of Patricia nodes as a proof of validity. Conclusion. The Ethereum protocol was originally conceived as an upgraded version of a cryptocurrency, providing advanced features such as on-blockchain escrow, withdrawal limits, financial contracts, gambling markets, and the like, via a highly generalized programming language. The Ethereum protocol would not support any of the applications directly, but the existence of a Turing-complete programming language means that arbitrary contracts can theoretically be created for any transaction type or application. What is more interesting about Ethereum, however, is that the Ethereum protocol moves far beyond just currency. Protocols around decentralized file storage, decentralized computation, and decentralized prediction markets, among dozens of other such concepts, have the potential to substantially increase the efficiency of the computational industry and provide a massive boost to other peer-to-peer protocols by adding for the first time an economic layer. Finally, there is also a substantial array of applications that have nothing to do with money at all. The concept of an arbitrary state transition function, as implemented by the Ethereum protocol, provides for a platform with unique potential, rather than being a closed-ended, single-purpose protocol intended for a specific array of applications in data storage, gambling, or finance. Ethereum is open-ended by design, and we believe that it is extremely well suited to serving as a foundational layer for a very large number of both financial and non-financial protocols in the years to come. Whew. All right, it's finally over. We've made it to the other side. If you made it this far, I commend you. That certainly took a lot of brain power, and I didn't understand every little aspect of it, but even the things I didn't pick up on, there's little kernels, little nuggets that I absorbed through osmosis, and hopefully you did too. If you're listening to this on the bus, on the train, on your way to work, if you're out for your jog, if this was helpful to you, I'm just here to try and add some value to the community, as so many other folks have done that I've benefited from. If you're feeling generous, you can always drop something in my tip jar and hit that subscribe button so you get notified when I post more white papers. This is Giovanni Pickle signing off. Peace.